Okay, so module 24 on problem solving. I think you'll like this module because we're not only going to give examples of various puzzles, right, that are well known and that research has been conducted on, but we'll also talk about human models and non-human models. So we do have some interesting studies that have been done in the primate world with this too. So in this module on problem solving, we have 3 questions that we want to answer. The first question is, how do people approach and solve problems? Because there are different ways to look at problem solving. And so we're going to talk about, from a psychology perspective, how people actually approach a problem, and that may have an effect on how they solve their problems. The second question is, what are the major obstacles to problem solving? Problem solving is not always just black and white. There are sometimes ways to go about that. And then the third question we have is, what is creativity? Because that has a big part of problem solving also that we're going to look at in this chapter. All right, so one problem solving technique that we have is called the Tower of Hanoi. You may be familiar with this, you may be not familiar with this, but you can find this, we're going to show it and we're going to talk about it then more so on page 244 in your text. So the Tower of Hanoi looks at different things. So the way people go about solving puzzles helps illuminate how they solve complex real-life problems. So you may have noticed that if you were playing, some sort of puzzle type game, maybe that is Clue, maybe that is Catan, or something like that. And the way that people solve puzzle problems, whether it be one of those board games, is also the way that they may solve problems in their real life experiences. Psychologists have found that problem solving typically involves 3 different steps. Okay, so there are 3 steps that psychologists have found to solving problems. One is they prepare to create some sort of solution. They prepare to create some sort of a solution. The next thing is that they produce a solution, and then they evaluate the solutions that have been generated. They prepare to create the solutions, they produce the solutions, and then they evaluate the solutions that they generated. So this is a 3-step process that typically is how problem solving is looked at. Now, the Tower of Hanoi puzzle is a good way to illustrate this 3-step process. This slide is looking at the Tower of Hanoi. Now, you may not have known this was called the Tower of Hanoi, but probably a lot of you have played something similar to this. So it says at the bottom, the goal of the Tower of Hanoi puzzle is to move all 3 discs from the first position to the third and still preserve the original order of the discs, using the fewest number of moves possible while following the rules that only 1 disc at a time can be moved and no disc can cover a smaller one. Okay? So do you hear what I just said? You have to take it from position 1 to position 3. Okay? And it says that the rule that 1 disc at a time can be moved and you cannot have a larger disc on top of a smaller disc. Okay? So here's the start and here's how it needs to look in the end. So you need to do this without obstructing those rules. That is the Tower of Hanoi. And your book talks a little bit about the Tower of Hanoi also, but it gets a lot into, trying to figure out how you're actually going to do this. At first, it's probably going to be quite difficult. And you're probably going to make some errors because, again, you have to follow those rules. But once you figured it out, it should get easier and easier as time goes on. Now, figure 2, this is at the top of page 245, and this shows you 3 steps, as we talked about, that are involved in problem solving. So 1 is the preparation, right? We said there was preparing to create the solution. Therefore, you have to understand and diagnose the problem. The second part is the production. As we mentioned, that is producing the solution. So you have to generate various solutions. And then the third step is the judgment, right? And that is where you're evaluating the solution. If you think about this, when I go through this and I teach this, I always come back to, let's say, an emergency room doctor. And they have a case that comes in, and they have to go through these 3 steps. They have to understand and diagnose the problem. Then they have to figure out, okay, how are we going to solve this problem? And then the third step is actually evaluating your solution. Was this the best way? It could be quite dangerous if you get to step 3 and you realize it wasn't the best way, because therefore that person may die or you may have other issues that come about. But this 3-step process in problem solving is very dire and a very good problem solving aspect to look at for any doctor who works in an emergency room situation, or perhaps for a surgeon. They have to also go through this 3-step process of how they're going to carry out this surgery. All right, so let's look at each of these individually. The first one is the preparation, understanding and diagnosing the problem. That was the first of those puzzle pieces in the previous slide. So you may have 2 different problems. You could have a well-defined problem, or you could have an ill-defined problem. First off, the well-defined problem. The nature of the problem and the information needed to solve it are available and clear. That's a well-defined problem. You know exactly this issue, you've dealt with it many times, and you know how to go about solving it, right? So if someone comes in with a broken leg and it's a basic break, you know exactly how to solve the problem and fix the break, okay? However, you can also have ill-defined problems. The nature of the problem and the information needed are unclear. So perhaps someone is brought in and they have these symptoms that you are not familiar with, and you aren't sure, what the actual problem is. So now it's going to take a little bit more in-depth research into trying to find out how to diagnose the issue, right? Because it's not a well-defined problem that you dealt with before. It's an ill-defined problem. So you can have 3 different kinds of problems. One is called an arrangement problem. Okay, an arrangement problem. This requires the problem solver to rearrange elements in a way that will satisfy a certain criterion. So this may be like anagram problems or jigsaw puzzles. If you've ever put together a jigsaw puzzle, this is an example of an arrangement problem. You can also have problems of inducing structure. And this is where the person must identify the existing relationship among the elements that are present, and then they have to construct a whole new relationship among them. So your book gives the example of this, and we'll look at this in the next slide also, the example that the book has. The third type of problem is a transformation problem. And this consists of the initial state, the goal state, and the method you're going to use to change the initial state into the goal state. So this would be like the Tower of Hanoi. That's a transformation problem. You saw the start, you saw the finish. You need now to come up with some sort of method from going from the start to the finish, right? That's the Tower of Hanoi. So arrangement problem again was like a jigsaw puzzle. The transformation problem was like the Tower of Hanoi. The next one we're going to give you an example of each of these, I should say, but you'll see this in the next couple of slides then. Okay, so this is figure 3A, and this is at the top of page 246. And this is an example of an arrangement problem. So with anagrams, right, if you've ever played Scrabble, that's like an anagram type of thing. So you rearrange the letters in each set to make an English word. That's like an anagram. You also have, let's say, this example that you see in the picture. So you have two strings that are hanging from the ceiling, but they're too far apart to allow you to grab both of them at the same time, or to grab one and walk to the other. On the floor, you see a book of matches, a screwdriver, and a few pieces of cotton. How could the strings be tied together, right? So you have to look at that and figure out that problem. So the second one is the inducing structure type of problem. And if you remember from the previous slide, we said inducing structure is you must identify the existing relationship among the elements that are presented and then construct a new relationship among them. Okay? So the first one is the anagram. That's the arrangement problem. You also kind of have this string one also. Now, if you go to this one, this is the transformation problem. This is like the Tower of Hanoi, so to speak, okay? So in this first one, and you can see this one also on page 246. Pages 246 and 247 are going to show you all of these. So this first one deals with water jars. A person has 3 jars with the following capacity. Jar A has 28 ounces, jar B is 7 ounces, and jar C is 5 ounces. How can the person measure exactly 11 ounces of water in those? And if you look on page 247, you'll see the answers to these, okay? You'll see the answers. I may have the answers on another slide also. Let me see if I do. I don't think I have all the answers, no, but if you look on page 247, you can see the answers to these problems. Now, you have another one here that deals with these coins, and it says 10 coins are arranged in the following way. By moving only 2 of the coins, can you make 2 rows that each contains 6 coins? So, are you able to move only 2 coins and make 2 rows with each row containing 6 coins? Again, if you look on page 247 in your textbook, you're going to be able to see the answer to that. I don't want to give it too easily, right, on the slide. I want you to think about it a little bit. The ones on the previous slide too, where we had the anagrams and then the screwdriver and things like that, you can kind of that'll show you the answers also on page 247. But these are transformation problems that you can see. So the other ones that we just looked at, those were arrangement problems, and then also the inducing structure, same as this. And then you have the transformation problems on this one. Now, the next slide is representing and organizing the problem. So there's 3 different ways that we do this. The first one is the way in which we represent a problem and the solution we eventually want to come to, that depends on the way the problem is phrased or framed. If it's phrased or framed differently, that could change the solution that you come to. So it really depends on the way that you ask the question, perhaps on the solution that you will use. So you want to consider the following problem. A man climbs a mountain on Saturday, leaving at daybreak and arriving at the top near sundown. He spends the night at the top. The next day, Sunday, he leaves at daybreak and heads down the mountain, following the same path that he took to climb up. The question is this: will there be any time during the second day when he will be at exactly the same point on the mountain as he was exactly the time on the first day? Okay? So again, a man climbs a mountain on Saturday. He leaves at daybreak on Saturday and arrives at the top at sundown on Saturday. The next day on Sunday, he leaves at daybreak and starts to climb back down the mountain. The question is, will there be any point in time on that second day on Sunday when he will be at exactly the same place on the mountain as he was at exactly the same time on the first day? They're both leaving at daybreak on both days. So this slide is answering that question, right? It says you can solve the mountain climbing problem by using a graph. So you see here on the x-axis is the time of day. The altitude on the mountain is on the y-axis. You have the bottom and the top, and you have sunrise and sunset. So it says, keep in mind that the goal is not to determine the time, but just to indicate whether an exact time exists. Consequently, the speed at which the traveler is moving is unimportant. Can you think of other approaches that might lead to a solution besides doing this graph? Okay, so you can see that this is where they cross. They crossed here at the time of day, going up, and they crossed at the exact same time of day, coming down. Okay? So that answers that question. But can you think of any other ways that, besides using a graph, that you may come to this same conclusion? Now, this is figure 6 at the bottom of page 267, or 247, excuse me, 247. The problem you have is, should you do surgery or should you do radiation? Okay, so this is always a question that arises, you know, the way the problem is framed. So it says the survival frame. Surgery. Of 100 people having surgery, 90 live through the postoperative period, 68 are alive at the end of the first year, and 35 are alive at the end of 5 years. With radiation, of 100 people having radiation therapy, all live through the treatment. 77 are alive at the end of the first year, and 22 are alive at the end of 100 years. Both of those said kind of the same thing, right? But it's a little bit different of the surgery and the radiation. Now, the mortality frame. So this is for more patients who choose surgery, and this is for more patients who choose radiation. For surgery, of 100 people having surgery, 10 die during surgery, 32 die by the end of the first year, and 66 die by the end of 5 years. This is saying the exact same thing. It just depends on whether you're looking at it from a survival mode or a mortality mode. Same exact thing is being said. For radiation, of 100 people having radiation therapy, none die during the treatment, 23 die by the end of the first year, and 78 die by the end of 5 years. Again, it says the exact same thing. It just depends on whether you're looking at it from a survival viewpoint or from a mortality viewpoint. Whether or not you choose surgery or radiation. These mean the exact same thing. Nothing has been changed. So it says the decision often is affected by the way a problem is framed. In this case, most would choose radiation over surgery despite similar results. They are the exact same results, but most people would choose the radiation over the surgery. All right, so that was all part, if you remember back to that slide where we had the puzzle pieces. I got to go back and find mine here in my slide. So preparation was the first one, right? Understanding and diagnosing the problem. The second puzzle piece was production, and this was generating the solutions. So we have it looking at this way. In place of trial and error, complex problem solving often involves the use of heuristics and cognitive shortcuts that generate a solution. Remember, you do have those heuristic errors, though, that you have to keep in mind. So in place of just doing trial and error, there's a lot of complex problem solving that goes into play. The means end analysis is used as a strategy in which a problem solver considers the ultimate goal, which is the end, and determines the best way to get there. Okay? The ultimate goal is getting to the end, and you're trying to determine the best strategy to get to the end. Each step is going to bring you closer to the resolution. So another heuristic that we didn't discuss yet is what is called sub-goals. So you're going to divide your problem into sub-goals, and then you're going to solve one sub-goal. That's going to get you to the next one. You're then going to solve the second sub-goal. That's going to get you to the next one, and so on and so forth until you reach that end goal. So you're going to solve each problem in those sub-goals leading up to the end solution. Okay, so continuing on with this production, and generating solutions, we have what is called insight. Insight is where you have this sudden awareness of the relationship among the various elements that previously appeared to be unrelated to each other. So you're looking at all the elements of the problem, and all of a sudden you notice something that you didn't notice before. And you're like, aha, this is going to help us, right? So this concept, or this phenomenon of insight, this was demonstrated in this well-known historical study done by Kohler. And he examined the learning and problem-solving process in chimpanzees. And we're going to look at this on the next slide then also. But what he found, or what it determines, is that subsequent research has shown that prior experience and trial and error practice in problem solving must precede some sort of insight. Okay? Prior experience and trial and error practice in problem solving must come before the insight. Okay, so this is figure 7. This is a study done by Kohler, and you can see this on the bottom of page 249. It also talks about this in the written section on page 249. But you can see, here's the chimpanzee, and his name was Sultan in this well-known study by Kohler. So here's Sultan, and he sees hanging from the top of the ceiling a bunch of bananas. And he wants to figure out, how do I get those bananas? I really want those bananas, right? But they're out of his reach. No matter how many times Sultan jumped, he could not reach the bananas. He then looks around and he sees these crates. So he starts to carry all the crates over to one position. He stacks them up on top of each other and is able to reach the bananas. Okay? So that is insight. However, if you remember what we just said at the bottom of the previous slide, is the prior experience and trial and error must come before insight. So Sultan must at some point in time knew what these crates were, knew that he could stack them on top of each other and then climb up to that, and that would be high enough to reach those bananas. So that trial and error, or that prior experience, came before the insight of knowing that I can stack all of these up and reach those bananas. But if you didn't have any prior experience with crates, or knowing that you could stand on the crates, if you piled them all up, the insight would not even be there. You would not even have used those crates. Okay, now coming to that last puzzle piece. I need to go back in my notes here and look at it. That last puzzle piece that we had was judgment. So far we've had preparation, that was understanding and diagnosing the problem. The second puzzle piece, the second step in problem solving, was production, and that was generating a solution. And then the third puzzle piece, the third step, is judgment and evaluating your solutions. Now, if there is no single correct solution, then evaluating your solutions can be quite difficult. In theory, if we rely on appropriate heuristics and true or valid information, we can make accurate choices among the alternative solutions, right? That is, if you rely on appropriate heuristics. So theoretically, that should work. However, there are several kinds of obstacles that bias the decisions and judgments that we make. So in theory, that should be great. There should be an appropriate heuristic and valid information, and boom, you should be able to solve the problem. However, life doesn't always work in theory. There's lots of obstacles and judgments that we make that do not help us. So what we have to do is we have to examine the bias in decision making and see how it has influenced the development of a new field known as behavioral economics. So what are the impediments to the solutions? Why is problem solving such a problem, right? Why do we have so much difficulty sometimes with problem solving? The difficulties encountered in solving problems often stem from how the problems are presented. That takes us back to that surgery versus radiation. They said the exact same thing, but they were worded differently. So that's one of the difficulties that we have. So the presentation of a problem can mislead you in the preparation stage. How it's presented can mislead you into solving it one way or another. So let's go ahead and look at this. This is this figure 8, and it's going to continue on with figure 9 in the next slide, but this is on pages 250 and 251. So here's the problem. The problem is to place the 3 candles at eye level on a nearby door so that the wax will not drip onto the floor as the candles burn. And you can only use the material in the figure, okay? So you see that we have some thumbtacks, we have some candles, and we have some matches. And our goal is to place them at eye level on a nearby door so that the wax will not drop onto the floor. Okay? That's the problem that we are presented with. Now, a solution to the problem is found in figure 9. It involves taking those thumbtacks, tacking the boxes to the door, and placing the candles in the boxes. See how we did that? Now you can put it at eye level on that door, and none of that wax is going to drip onto the floor. You had 3 different boxes, and each box had different things in it, right? So you're going to take the matches to light the candles. However, first, you're going to take the thumbtacks and thumbtack those boxes to the door. Now, continuing on this with this question, why is problem solving such a problem? The impediment to solving that previous problem with the candles is on functional fixedness. That's the tendency to think of an object only in terms of its typical use. Okay? We would not think of thumbtacking those boxes to the door, right? So a related concept is mental set. It's the tendency to solve the problem in a certain way based on our past experience. Well, what both of these do, this fictional excuse me, the functional fixedness and the mental set, the problems with both of these is that it hinders our ability to come up with other solutions. So you may have been trying to solve a problem previously, and you have such a mindset on how to do this that you become so fixated on it, or what are the functions of these various objects. And it hinders your ability to think of other possible solutions. That can then prevent us from seeing beyond what is the apparent constraint of a problem. So here we have another issue, right? This is figure 10 on the bottom of page 251. So given jars with these capacity in ounces, right? So it says, try this classic demonstration, which illustrates the importance of functional fixedness and problem solving. The object is to use the jars in each row to obtain the desired amount of liquid. So jar A has 21, jar B has 127, and jar 3 has 3. You need to obtain 100, right? So how are you going to do that? And then 99, and then 5, and 21, and 31, and 25, right? So you are so stuck on how you're going to go about doing that that you can't come up with the actual solution in doing it. It talks about how you can do this in the middle of page 251. It said if you had tried to solve the problem, you know that the first, oh, this is with the 5 jars. Sorry. I'm trying to find the one with the, oh, where's it talk about the one with the jars? I'm looking at the example here. I think it's going on actually without looking at the jars, because it doesn't talk about figure 10 in this one, which is very, very unfortunate. I can't see. It goes from figure 9 to then figure 10. Figure 10 also looks at this one, right? So this one is that the solution to the 9-dot problem, right? So this one is, it says a classic experiment demonstrates functional fixedness. As you can see in figure 10, the object of the task is to use the jars in each row to measure out the designated amount of liquid. Try it yourself to get a sense of power of functional fixedness. Now it says, oh, it does say in here, first fill the largest jar and then from it, fill the middle-sized jar, and then once you have that done, go to the smallest jar, which is left to be. And in the designated amount, stated as a formula, the designated amount is B, A, and then 2C. I think that's very confusing, though. I like going to this other one, though, with the lines, right? So this one's much easier, I think. Fictional fixedness is really the concept of mental set. Mental set is the tendency to do this, so on and so forth. For this one, you try to draw 4 straight lines so that they pass through all 9 dots in the grid below without lifting your pencil from the page. So you are supposed to take your pencil and you are supposed to come up with 4 straight lines that you can go through all 9 dots without lifting your pencil, right? And so you can see how they did this. The solution to the 9-dot problem requires the use of lines drawn beyond the boundaries of the figure, something that our mental set may prevent us from seeing more easily. So you see how you kind of had to go beyond that. So you could do that, then down through that, then up, then down. See how you went beyond? It didn't say you couldn't go beyond. So most of us would go here and then go here, up through here, and down through here. Well, now you missed these 2 dots. So if your functional fixedness is that you can't do it, you don't have the insight to actually go beyond those dots. There's nothing that said you could not go beyond those dots. Okay, so now we have, again, this why is problem solving such a problem? One thing that we have to think about is what is called confirmation bias. And this is the tendency to seek out and weight more heavily information that supports your initial hypothesis and to ignore the contradictory information that supports an alternative hypothesis or solution. That's what we tend to do, right? The reason why we do this confirmation bias is we have 2 different reasons why we do this. So again, confirmation bias was your tendency to seek out and weight more heavily information that supports your initial hypothesis, and then to ignore all the other information with this alternative hypothesis. And again, there are 2 reasons why we do this. One of those is rethinking a problem that appears to be solved already takes extra cognitive effort. And we tend not to do that, right? We tend not to take the extra cognitive effort. Because why would we want to exert ourselves more? We want the easiest possible solution. However, that may actually take longer, right? But we tend to think that rethinking the problem is going to take too much effort. The second thing is we tend to give greater weight to subsequent information that supports the initial position compared to information that is not supported in the initial position. So we tend to give more weight to the information that supports it versus information that does not support it. All right, I want to go on to this next part, which is evaluating others' conclusions. And this is the science behind fake news. We have heard a lot in the news within the past couple of years about what is called fake news, right? And so we need to evaluate these conclusions that other people came up with. And are we going to believe them or are we not going to believe them? So what we think about is that sometimes we draw these erroneous conclusions because others have actively attempted to mislead us. So when we talk about fake news, it is fabricated information that is made to look like and sound like really legitimate news. However, it's not. The intent is to persuade you to accept this false information. Researchers have found out that false stories are distributed more broadly than true stories. That's very unfortunate, but that's the way that it goes. One reason may be that the fake news is often more novel than true news, right? We know that something's true. It's been shown time and time again. Then someone comes up with this whole new idea, and that's very novel and interesting to us, and it gives us this different way of looking at it, and we're like, oh, well, that's really interesting. Maybe that's true. There, they just got you with that fake news. Whenever you know what the correct answer is. Okay, the last thing in this, in this module that I want to talk about is creativity and problem solving. So this will be on the next two slides, and then we'll be done with this module. So creativity and problem solving. When we talk about creativity, it's the ability to generate our original ideas or to solve problems in a new or novel way. We're being creative on how to do it. We're not going to just do it the same old way. We're going to be creative in solving these problems. Individuals who are seen as creative, they show divergent thinking and also cognitive complexity in their thinking. What we mean by divergent thinking is that you think that it's thinking that generates multiple and novel responses to problems or questions. I myself am not too much of a creative person, right? I don't show this divergent thinking. I tend to go with the way that it's always been done. I don't like change too much. I'm not really too much of a creative person in trying to find this new novel way of solving a problem. I kind of look at it as if it ain't broke, why fix it? Right? But there are some people that will try to come up with a new way to fix a problem. And so they have this cognitive complexity. It's this preference for elaborate, intricate, and complex stimuli and thinking patterns. Again, that's not me. I tend to take it as the easiest way, and if someone's already found the solution to the problem, why would I want to change that? That's just me, though. Now, when we think about creativity and problem solving, this divergent thinking that characterizes creative people contrasts with what is known as convergent thinking. And that is thinking in which a problem is viewed as having a single answer. That's probably more me. I'm probably more of a convergent thinker than a divergent thinker. May not be good. That's just the way that I look. So this convergent thinking produces responses that are based primarily on knowledge and logic. I don't need to come up with different ways, right? There's already an answer that's been found. It's very logical. Why would I want to come up with this other new way? Now, your traditional intelligence tests, we'll talk about intelligence in the next chapter. But your traditional intelligence tests tap convergent thinking skills. So if you're a divergent thinker, you're not going to be seen as highly intelligent because the questions that are asked on those intelligence tests are geared more towards the convergent thinker. And so highly creative people may therefore find that these traditional intelligence tests, they actually penalize their divergent thinking. And we'll get into that a little bit more then whenever we get to chapter 9 on intelligence.